Thank you for the introduction, Michael, and welcome. Uh, so I'm going to talk about time series switch engineering done right. And just to add a little bit of color to my background, uh, I started working at Agnic after graduating from grad school, and I worked on vehicle health prognostics and driver behavior analytics. And we were working on streaming data from the cars a few years back then. Uh, After spending a year working on NLP problems, I moved on to identified, where I was working on certain problems related to record linkage. And since then, Identified was acquired by Workday, and I have been working on predictive analytics for Workday ever since. And in particular, we have put two applications in production, which are retention risk prediction and the yeah, that's better. Retention risk prediction and the customer collections. So we'll talk about a few lessons that we learned over the course of last few years as we proceed. So we are going to talk about a particular class of predictive classification problems, and it's a subclass of problems that we encountered while at Workday. And retention risk prediction is a interesting representative of this class. And we are not going to talk about retention risk by itself, but we are going to use it to illustrate the ideas that underlie these kind of problems. We'll talk about how we formulated this problem and the validation methodology we had to use. And finally, we'll talk about feature engineering, and then I'll conclude. So as we are going to use retention risk as our illustrative example, let's talk a little bit about retention risk. So we want to quit. Who is going to quit in next 3 months for a given company? And so taking a step back, Workday is a cloud-based provider of HR and finance software. And we have over 1,000 customers who use our services. And Workday's SCM application tracks transactions. These transactions are related to employee hirings and terminations, performance reviews, pay raises, stock grants, promotions, etc. Question is, can this transaction history be leveraged to deliver more value to our customers? And retention risk was our first attempt in that direction. And a little bit of terminology. So when I say worker, actually mean an employee. Active means employee is still employed with that company, and terminated means that employee quit. All right, so let's see what kind of problem this is. So is this a historical classification problem? Are we trying to classify people who, we have some history of transactions. We have Roger, Corey, and some transactions for them. Are we trying to predict, or are we trying to separate who quit and who did not quit? That's a legitimate question to ask, and it could be used to identify things like what are the drivers that are causing people to stay or quit. But that's not our goal. Our goal is to predict who will leave. That is, Roger will leave, and predicting that is our goal. All right, so this is a forecast, like a time series forecast. And you can look at this time series of data. The blue data is historical data, and the red dashed line is our prediction. And the gray fuzz is the confidence intervals around that prediction. So what we want is really a forecast. Now, so let's go through a simulated timeline to frame the problem that we want to solve. And well, we are trying to solve a predictive classification problem. We are looking at Jim, and Jim is a great employee, and his employer wants to know if Jim is going to quit in next 3 months. And we chose to formulate this problem as a supervised classification problem in a predictive context. There are other ways to formulate this problem. For example, survival models. But after some initial exploration, we settled on the supervised learning as the appropriate way for us to proceed. So let's go through a similar timeline just to see just to set up the problem. So here is Jen. A year back, she received a raise of about $5,000. Then she was transferred, and she received another raise of $7,000. Here is Mary. She was promoted around sometime last year. And now Mary starts to report to Bob. The rumor is that Bob is a terrible manager, and a lot of people who report to him quit. And sure enough, Mary left soon after. Now, Jen is reporting to Bob. Is Jen going to quit soon? That's the question that we want to answer. So again, it's a forecast. Based on what we have seen till now, we want to predict what will happen. So for workers who are active today, we want to predict who will quit in next 3 months. So we have this +3, that's our prediction horizon. And based on what has happened till now, all the transactions that we have seen, we want to predict who will quit or who will not. That is, we want to fit a function f based on data x that will allow you to predict who is going to quit and who is not. All right. It's almost a Markov-like assumption. Our hypothesis is that we can, in a feature matrix X, we can capture everything that has happened to date that will allow us to predict what will happen in next few months. All right. So here is the timeline again. And what are we predicting? Whether Jen will quit or not. So let's go over our hypothesis. Let's imagine that we sit in a take a time machine and we go back 3 months. We have forgotten everything that has happened in the last 3 months. And we only know what has happened till that point, till 3 months back. And our hypothesis is that what has happened till this point is to a large degree going to determine who is going to quit and who is going to not quit. That is, the fact that Jen is going to stay active and Mary is going to leave was determined by what has happened in the past. All right, and so how do we? Again, we said we are going to frame this as a supervised learning problem. So where are our training labels going to come from? We are almost setting it up as a parallel version of today. Sitting here today, we want to predict 3 months in future. Similarly, we are going to step back 3 months and we are going to decide based on who quit and who remained active in last 3 months, our data labels. All right, so that's our Y. And where is our X, the feature matrix, going to come from? It's based on what has happened up to 3 months back. Okay. And we are going to go with a single feature for illustrative purposes. The feature is, do you report to a bad manager or not? And for Mary, that feature takes value 1, since she reports to Bob. And for Jen, that feature takes value 0. And we fit a model based on these X and Y, the feature matrix, and the prediction. All right. So now we need to make a forecast. And we need to make a forecast for Jen. Mary has quit, and we no longer need a forecast for her. But wait a minute, didn't we train for Jen? And we are again predicting on her? I'd argue that we didn't train on the same Jen that we are making a prediction on. We trained on the Jen as of February. She was a happy camper. Jane of today reports to Bob, almost a different person. All right. And by the way, this is very similar to autoregressive time series models. All right. So, and when we extract features for Jen, sure enough, now the feature takes value 1 for Jen because she now reports to Bob. And hopefully our model is going to predict that Jen is at risk. All right. So how did we fit a model? We held back everything that happened in the past 3 months, all the transactions, and we build our feature matrix X bar based on that. Our labels came from people who quit or did not quit in the last 3 months. A little bit of terminology, I'm using the overbar to indicate that we are actually using this data to fit a model. All right. So now we make a forecast. The feature matrix that we plug in into the model X came from all the transactions that we have seen up to this point. Now remember that when we compute X, we are only looking at people who are active today. All the people who terminated, we don't need to make a prediction for. So, and we plug this in into our model, and we are going to get a forecast. So, how do we validate this model? How do time series models get validated? So, from our illustrative example, we see that we are trying to make a prediction here 1 year in future. And here we are looking at, we hold back everything that happened in last 1 year, that is this window. And we train our model based on the data we have seen before. We make a prediction and we check it against what happened in the last 1 year. Fairly standard time series stuff. Our validation strategy is going to be inspired by the same methodology. So we hold back everything that has happened in last 3 months. That's our ground truth. And that's what we are going to hold ourselves against. We train our model based on the people who quit or did not quit between 6 months back and 3 months back. So that's where our Y labels are coming from. And our feature matrix for training, X bar, is based on everything that has happened before 6 months. All right. Now we make a forecast. We had a model that we trained, and we are going to, for all the people who are active at 3 months back, we are going to create a feature matrix based on all the transactions we have seen. We are going to plug them into the model, and we are going to get prediction Y hat. And we are going to compare that against the ground truth. And that's how we are going to compute our metrics and judge the quality of our model. So there we go. So since I like pictures so much, I'm going to take another timeline. So here we have our old friend Mary at the bottom. But at top we have Joe. Joe had a very similar timeline. So he had a raise a year back, but he started reporting to Bob soon after, and he left pretty soon. So, as we said, we are going to hold back everything that happened in past 3 months, and we are going to train our model based on what happened between the period of -6 months to -3 months. And that's where our labels are going to come from. So for Joe, the label is 1 because Joe quit, and for Mary, it is active. And what are our features? So feature matrix X is based on everything that has happened in past 6 months. And for Mary, the feature took value 0, and for Joe, the feature took value 1. That's how, and we fit our model. And now we make a prediction for Mary because Joe has quit, so we don't need a prediction for Joe. But for Mary, we need to make a prediction based on what we have seen till 3 months back. All right. So the feature will take value 1 for Mary in the validation period, and our model will say Mary is at risk. And sure enough, Mary left, and we get to count that as a false positive or as a true positive. All right. So here is a not such a happy case. Here is Jack. Jack started to report to Bob in our ground truth period, right? And he left pretty quickly after that. And when we generated features for Mary, the feature had value 1 for Mary, but 0 for Jack. Our model is going to say Jack is safe and Mary is at risk. And sure enough, Jack is a false negative for us. And here we have an important point. Based on what we knew 3 months back, we had no reason to believe Jack was at risk. But stuff happens. And that's why predicting future is harder, like Yogi Berra said. So going back, we call this methodology temporal validation. We train based on, for our training, we generate our feature matrix based on what has happened till 6 months back. Our labels Y came from what happened between 3 to 6 months back. We build our model. We made our forecast based on the feature matrix X that we extracted, based on based on transactions till 6 months back. We made a prediction, and we validated that against the ground truth. So that's our methodology. So why did we have to invent this methodology? Why could we not go with standard k-fold? What is the fundamental assumption behind k-fold validation? That your labels Y are independent. There's an IID assumption there. And in our case, the labels are not independent. So I have an example here. Jack and Jill are friends, and a fact that is not captured by our features. But when Jill quits, Jack's retention risk spikes. So the labels themselves are not independent of each other. There's a dependent structure here. And the data itself is not stationary. Due to market forces and other external factors, the attrition rates change as a function of time. So the temporal validation methodology, which prescribes peeking into future, allows you to do reliable predictions that k-fold will not allow you to do. All right. You need more data? You want to capture seasonal effects? Sure, we do what we always do, which is slide windows backwards. So we got our first data set by looking at 6 months back, like we did. The X1 bar came from looking backward 6 months. Y1 bar came by looking at between 6 to 3 months. We got more data by sliding back by 3 months. And now Y2 bar, which are the labels, came based on what happened between 9 months and 6 months back. Now remember that people who terminated between this period will not survive for the next window, right? And then we take a union of these Xi's and Yi's, and we train our model based on that. All right. And we forecast in the usual fashion by looking at what has happened till 3 months back, and we validate it again in the same fashion. All right. This is similar to non-overlapping moving block bootstrap methodology that is used quite commonly in time series forecasting. All right. So there's one more thing that we cannot forget. There are non-stationary effects. As I said, the retention risk change at different times is different. And so we have a heuristic for dealing with that. We generate our metrics for last 12 months. Same methodology. We simply slide the window 1 month each time, and we generate our quality estimates. Here I'm showing AUC ROC as our quality estimate with some simulated data. And then we looked at 75th percentile. That is this little red circle. I have marked by a little red circle, and we use that as our estimate for our quality of our models. And now that we have done all this, we have a solid foundation to do feature engineering. So this is the done right part of my talk. Till now, till we had set up the right methodology for validating our models, we could not proceed in a scientific fashion with our feature engineering. Because when we started, we actually tried to fit a model using K-fold, and we got really great results. But those results were misleading. And till we actually fixed our methodology to be right, all our feature engineering was essentially worthless, because K-fold methodology was picking into future, and we were getting results that were artificially inflated. We could never get those kind of results in reality. And that's why it is crucial that we set our validation methodology the right way. Now we can start talking about features. Any questions till now? Yes, sir.
Any tree-based model?
We did use tree-based models.
What about the drawbacks if you would have done that, like random forest GBM?
So there's no drawbacks per se. The linear models actually gave us performance that was comparable to tree-based models after our feature engineering, and it's just slightly more efficient and easy to fit linear models. So, but there is no commitment till this point to how you fit the model. You could use random forest methods, you could use neural networks, you could use linear models, you could use whatever. The methodology doesn't change. How you fit the model, that function f of x, as I was talking about, can change. But what we're talking about is the methodology itself for validating and going forward with feature engineering.
What validation if you would use other models, non-time series?
So there are other kind of models, like survival models. We would still have to validate them in a fairly similar fashion. The feature engineering for them would proceed in a very different fashion, but it's still a prediction, right? It's still a forecast. You cannot validate it by not validating against what actually happens based on feature. You cannot allow information about what happened. When we train a model, we cannot allow information from future, so to speak, leak in. Otherwise, your results are just going to be inflated. Yes, sir.
Was it important that the window be non-overlapping, or could you have used a sliding window to get a little bit more training data?
Oh, absolutely. So in one of our applications, we actually do use overlapping windows. It just was beyond my PowerPoint skills to actually draw it out. But it's a perfectly legitimate way to get more data. Yes, sir.
So imagine if Bob had started in October. Would you have used any of the data before October to train?
I'm sorry?
Suppose Bob, right, started in October, right? Would you have used any data before that to train?
So, I'm not sure I understand your question correctly. So, are you saying that from, let's say today, let's say that we are making a prediction today, you are saying Bob started in October of 2016?
I'm just referring to the timeline you had, right? You had May 2015 to May 2016, correct? So suppose Bob started in October. Would you have used any of the data before then to train, right?
For Bob, we are basically training a model based on for everyone, a single model for everyone.
Okay, so the thing I guess I'm trying to ask is, the reason why everybody's leaving is because of Bob.
Yes.
So I'm wondering if you are going to be using any data before Bob joined to train.
So I think that was a more of an illustrative example. But if Bob joined and you didn't know that he was a terrible manager, then obviously you cannot build that feature that Bob is a terrible manager, right?
Hi, thanks for sharing your methodology and stopping us fall into some of these traps. I noticed that the first kind of data at the beginning of your timeline is included like the most often, and it's sort of, as you go forward, it's included less and less. Do you find that your models have sort of overtrained for the earlier data, even though it's the furthest away from what you're trying to predict, and how do you control for that?
So one way to do that is we assign different weights, and historical data gets, the weights for getting the old historical data right are decayed. So that allows us to give ourselves less points for fitting the historical data. It's also actually sometimes important that if there's a data has seasonal patterns, to slide back in a similar time of the year last year. So, but yeah. All right. Sorry, go ahead.
The feature that you used for the model, was it specific to Bob, or was it just indicating a change in manager in general for the people?
So as an illustrative example, we use that Bob is a bad manager. And so in that case, yes, it was a feature sort of that was based on Bob. But we'll actually see what features actually went in our production model pretty soon. Right. So I think, let me talk about what features we used going forward. So, all right. So, all right, it's working. So we started with a few simple features. One of the features we started with is tenure, how long employee has been around. Another feature was time since promotion. We had a few other features based on number of promotions, how long it took you to between promotions, number of pay raises, was this employee hired for acquisition, the employee's performance ratings, the manager's performance ratings, and so on. These simple features did not give us a lot of lift. So the intuition is that a lot of features that are useful turn out to be time-dependent features. So let's take an example of hired through acquisition. So this feature was included because our customers were very certain that whether an employee is acquired or not has a very strong impact on attrition. We put it in our model, and it didn't show up. It didn't show up with any kind of weight, right? What went wrong? So we started thinking a little bit about it, and what we realized was that we had to slice this feature into features like this. So time since acquisition between 0 to 12 months, between 12 to 15 months, 15 to 24 months, and 24 to 27 months. Any guesses which features were strongly correlated, positively correlated with retention or attrition? That feature is actually strongly correlated with people staying. The feature that are strongly correlated with people leaving are time since acquisition is between 12 to 15 months and 24 to 27 months. That's where the people's dogs vest. And the time since acquisition between 0 to 12 months and 15 to 24 months actually are strongly correlated with people staying, because they have stocks to vest. Another feature that turned out to be useful was will your 2-year window since acquisition happen during our prediction window, because there are people who apparently live on the day their stocks vest. So other kinds of features that are also time dependent. Have you taken lots of one-day PTOs or days off recently? I guess you have been interviewing. All right. And And then we have interactions and external effects. So we have few features like pair range penetration, which essentially measures how well are you paid compared to people who are the same job title. So and historical attrition rate under manager, historical attrition rate under org. So we'll talk a little bit more about this feature in particular. And so this feature by itself wasn't very powerful, but when we started looking at cumulative attrition rates in 1 year and last 2 years, those started to be more useful. And org is a department, you can think of it as a department. In addition to that, almost a derivative of these two features turned out to be very useful as well. The attrition rate between 0 and 1 years and 1 to 2 years. That was pretty useful. Also useful was the derivative, essentially, of these two features. Is the attrition rate in your org increasing or decreasing or staying constant? And all of these features turned out to be very useful. So in the end, we put together a data pipeline for doing these things. Right at the beginning, we partition our data. Then we do feature engineering, model training, and validation. Getting this pipeline, ensuring correctness of this pipeline was an adventure, and it's a subject for another talk. In summary, we initially formulated the retention risk forecasting problem as a classification problem using k-fold validation, and the prediction quality did not match our expectations in customer trials. And we realized that the independence assumption was broken. And we extended the time series validation methods to temporal validation. And now we have 2 apps in production based on temporal validation methodology for over 100 customers. And the lesson we have learned is temporal validation results consistently match what we see in reality. And also the lesson that we have learned is base features that we include in our models are often time independent. So the takeaway is that if you have a forecasting problem or forecasting classification problem, be very careful about your methodology. In some cases, k-fold is going to work just fine for you. But there are times when you really need to look at the temporal validation methodology. And cool. So I think this slide is required by law in Bay Area. We are hiring. If you're interested, please come and talk to me. And any questions? If I have time for questions. Thank you. Yes, sir.
Did you find that you were able to train a single model that worked for a variety of companies, or did you have to train, use new training data for each individual customer?
So the way our legal contracts are structured, we cannot use data from one customer with another customer. Our legal language is ironclad, so we have to train different models for different customers. Yes, sir. Yes, sir.
Hi. So you mentioned that one of the other approaches that you were looking at was survival curve analysis, but ultimately you chose to treat it as a classification problem. Can you talk about sort of why you made that decision? What didn't work about survival curve analysis, and how did you validate that the classification approach was the better approach relative to survival curve?
So we basically, let me take the second part first. We validated based on our predictions. We made predictions using both methods, and this method turned out to be useful. My intuition is that this kind of data, this kind of problem is so event dependent that you are quitting because it's 2 years since your acquisition, and so on. So including all these time-dependent factors into survival models makes them really hard to scale and work. But it's a really longer discussion that we can have later, why the survival models didn't really work. Okay, I guess I'm out of time. Sorry.
Thank you, Parag.
Thank you.
And I guess I have one more takeaway from you.